Hi guys, greetings from Seattle. As I mentioned in my short, I was using my 6-inch trim saw from High Tech Diamond as a slab saw, and obviously used too large a rock, pushed it a little too hard, and my machine is now kaput. So my machine is out of warranty, and if you are familiar with High Tech Diamond, they do not sell replacement motors. They actually prefer that you send your trim saw in, and they will take a look at the electronics and replace everything and send it back to you. I think it's a flat fee of $175. I'm not sure if they charge more than that. Maybe somebody can ring in on that. And then you also have to pay somewhere around $60 for shipping back and forth. So because this is out of warranty, I wanted to take a look at what my options were for trying to replace this motor. But I thought I would also just kind of walk through my initial troubleshooting techniques. So like I said in the short, obviously the first thing you want to do is check the fuse located at the back of the trim saw. So it's where the power cable goes into the bottom of the trim saw body. You'll see a little plug there with a flathead Phillips screwdriver, and that's where this fuse is located. So in my case, I replaced the fuse and the machine still wouldn't restart. So I knew that I had issues somewhere else with a short in my system. So I flipped the thing over and I started just looking at the internals of what the trim saw components look like, and it's actually a very simple circuit. Other than power coming in this fuse, there is a speed controller for the motor and the motor itself. So the next check was to take a look at what the component for the speed controller was. I thought maybe that this had some kind of a rectifier in it, since I know that this is a DC motor. And I have AC going into it. So once I pulled the information on this is a KB Electronics speed controller. You can easily see that there is no rectifier in here. It's not an SCR. So I knew that somehow this motor had to have a rectifier that converts it from AC to DC. So this motor is available from other manufacturers. I think this same motor is what is used in an Ameritool or Covington 6-inch trim saw. I want to say Durable. I'm not sure about that. Durable from Rio Grande uses the same trim saw. There's another semiconductor manufacturing company called Allied High-Tech Products that sells replacement motors. And so that could be an option for you if you find that, you don't want to, work on the motor yourself. You can replace the motor. I want to say it's probably $160 to buy the motor from Covington, and then you can do the work yourself or have another electrician do the work for you. But, with High Tech charging $175 to do all the work, plus it's under warranty and you're paying shipping, I wouldn't buy the motor itself for $160. I'd rather just have High Tech do it. So I was considering that when I looked at the internet and started looking for replacement motors, and there's not a whole lot of information on the motor. When you see it, you're going to get, you're going to see this exact same label, which doesn't have any kind of part number on here to refer to for trying to find a replacement motor. So I think this is just a very specific, could be proprietary, I don't know, motor that you cannot find easily on the internet. So I noticed that there was a label underneath here. So, I'm just going to point out, this is 115 volt DC motor that pulls 100 or 1.6 amps, right? So when I pulled this label back, I was just curious what the nameplate was underneath this label. And that's what I showed in the short. So this actually shows that this is a 115 volt AC motor, and it actually has a part number on here. So if I had to replace the motor, potentially I could source a 115 volt AC motor. But I still had the question about, how is this thing getting converted to DC voltage? And so I took this apart, and which is very simple. It's just 2 bolts. It's there's some covers here. I don't know what the other holes are. I'm not electrical, my degree or anything, so I was just kind of winging it. But I unscrewed the 2 long bolts. So these are long bolts that basically hold the 2 end caps together. And so it's very easy just to unscrew those 2 bolts, and both the top and bottom end caps are holding the bearings in. So once you pull these out, or I can't get this out. So once you pull the bolts out, you can actually pop off the covers fairly easy. This plastic is just a removable gasket. There is a spring inside that you do not want to lose. So there's a spring that you put basically inside the cap, and it sits on the bearing to keep everything compressed. So you don't want to lose that. And so once you pop that off, the end cover comes off as well. So when you look at the wiring, there is a ground wire that I physically removed from here just to get it out of the way. So there's a ground wire that's attached to this screw that you'll have to unscrew, and then you'll be able to take this rear cover off. And so when I opened it up, you can definitely see this is not a brushless motor. This is a brush motor. So there are 2 brushes. I did pull the brushes out. So these are the brushes. They look like just standard carbon graphite type brushes that you can either replace or you can resurface. There was a little bit of carbon dust in here from the brushes, so I'm not sure why this is a totally enclosed brush motor where you can't replace the brushes or have access to them, because it does create some amount of dust that can spark the motor. So just some quick things to note. This is a PMDC, permanent magnet DC motor, so it doesn't have a wound stator. So it's just an armature rotor that spins because of the north and south pole magnets that are basically in the housing. And then there is a commutator on the armature, and then 2 brushes. So as the armature is spinning, because of the magnets, you've got current that is actually traveling, collecting in this brush, and then it basically comes back in. So this is the positive side, and this is the negative side. So my armature was dirty. It didn't look like these brushes were wearing evenly. So I've already, pulled the armature out and cleaned up the brushes a little bit. I still have a little bit more grinding to do. But, and then the other part is, you can pull this armature out, and there are plenty of videos out there to show you how to check your windings on the armature itself to know if this is grounded. So I checked everything on the armature, cleaned it up. There is no issues with the armature. And so that brings me to the rectifier. So the rectifier is very uncommon, I think. It's not totally out of the realm of manufacturing to mount a rectifier in a motor like this, but it just makes it very difficult to maintain. So if you end up having a failure, so you can't get to the brushes, you can't get to the rectifier if the rectifier blows. So I'm kind of glad that I did not reorder or reorder another motor or send this to High-Tech, because I don't want the same motor that has this failure mode. So I don't like the fact that I can't pull these brushes out, and I don't like the fact that you've got just a rectifier that's located inside of your motor that you can't get to, when this type of rectifier is well known for being very easy to blow a diode on it. So there is a I don't know if you can show, if I can show it here, but I'll show a clip in the video of this where you can actually pull the model number on here. And so the model number shows that this is a 10 amp rectifier. So it can take 10 amps and it can take 1,000, I think up to 1,000 volts per the model number that's on here. And it's the amperage that is the problem, especially on this type of a rectifier. So I'm going to show you guys how I troubleshoot these rectifiers, and let me get that set up in the next video. Hold on. Okay, so I went ahead and I pulled the armature out so I could show you what I've done. So this is the end that you attach the arbor to, and then this is the end that is basically the flat side of the motor. So there is a bearing that sits on here that I pressed off just so that I could access the commutator more easily for cleaning. Like I said, if you go out on YouTube, you can find videos that show you how to check the integrity of an armature. So you want to take a look at, you know, each of these individual plates on the commutator, and you can measure them side by side to make sure there's not a short between the two of them. You can check for continuity between the shaft and the commutator. I think you can check also between the panels on the commutator and the panels on the windings of the armature itself. So there are a lot of different things that you can do to check the armature to make sure that it has good integrity for continued use. And so that's what I've done. This armature is perfectly fine. So like I said, that brings me back to the rectifier. And I thought I would kind of just show you guys a quick little diagram of how a typical rectifier works. So a rectifier is really just 4 diodes that are put together. And so I kind of oriented this rectifier diagram to kind of indicate the same thing as what's shown on here. You have 4 terminals that you attach wires to. And between each pole, each terminal is a physical diode. So what the diode does is it allows electricity to only move in one direction. And so it's basically forcing all of the current to the DC power plus positive side. So you've got 2 alternating current wires. So that's these 2, the black and the white wires, that are attached to 2 poles, 2 opposite poles of the rectifier. And then you've got 2 DC poles. So there's a wire that's a negative DC and a positive DC wire. So your 2 AC wires are coming in at 60 hertz. So it's flipping back and forth, positive, negative with AC. And so it's meant to force current in one direction to the positive DC. So I'll show you, you've got the black and white wire coming in, you've got a red wire for DC, and then you've just got a plain open wire for the negative side. And so, you know, basically what the circuit is once you fed alternating current in, it's the positive side is actually measuring the motor, and it comes back to the negative side. So what happens is, you know, when you're cutting a rock and you bind your blade on the rock, it gets stuck, the motor is still trying to turn and it's not spinning. So you'll end up getting a spike because all of this resistance, it's basically built up resistance. That blade that's not spinning is extra resistance on the motor. So you end up spiking your current, and it blows one of these diodes. So these diodes, like I said, on this particular model are rated at 10 amps. So all it takes is a spike greater than 10 amps to blow one of these diodes, and you're done. You've got to replace your rectifier. And also with that, I mean, that's the whole reason why the fuse is installed in the system, because once the fuse is installed in the system, then, you know, it's a short circuit and you're basically feeding AC through everything. So, all right, so that's just the quick interpretation of what this is. So keep in mind, this is basically, a rectifier is just 4 little diode circuits that are potted into this connection. So when you take a look at the wiring coming in, I know it's hard to see. So this is the positive terminal, DC positive. This is the DC negative terminal. And then these two wires that come in are your two AC currents. So you've got a black wire that is attached to this bottom terminal, and then the white wire AC is attached to the top terminal of the rectifier. So in order to check this, all you've got to do is measure continuity across each diode. So it can only flow in one direction, so you should see resistance in one direction and then infinity in the other direction. It can't flow the other direction. So if you put your multimeter on the continuity setting, so you're seeing wide open right there, infinite, no continuity, and then you just check one by one. So let's look at the negative DC going to the white wire, which is AC. So I will actually put my negative multimeter on this wire, and I will touch, see if you guys can see it, touch the, all right, there, see, and so you're seeing 569 going through that circuit. So if I swap these, so you see flow is going in one direction, so if I swap these and do the same thing, right? So swap my leads of the multimeter and touch this, I'm not getting any flow. So that's telling me this diode is still good. So now we'll check this diode. So basically from the white alternating current wire to the positive DC. All right, so I'll leave this on the white wire, the positive, and let me put the negative of the multimeter on here. And they should be about the same. So this is showing, the other one was showing 569, this is showing 570. So I've got flow going in that direction. Let me swap these and see if we don't get flow or if we do get flow. And I don't have flow, so that's good. So this diode is still good. All right, so now let's check this bottom circuit. So we're gonna check this diode going from the negative DC to the black AC wire. So let me swap and let me put the negative of the multimeter to the negative of, or to this AC wire, and then I'm gonna touch the negative DC and see if we get any flow. And so that's actually a little bit higher, 582. So the top was like 570, this is 582. Close enough for government work, but it should be somewhat close. I would say that's close. All right, so if we swap these, and I put the positive multimeter terminal here, and I put the negative multimeter, I should get nothing, and I get nothing. Okay, so I've got 3 diodes out of 4 that are working, so now I just need to check the 4th one. So we'll leave this connected. So now I'm gonna go from the black wire, I'm gonna check the diode that's between the black wire and the positive DC terminal. All right, so I've got the black wire here. I'm gonna touch this, see if we get any flow. And that's not good. So I should either have a big number like 567 ohms, or I should have a 1. And this is showing me that there's something wrong with this diode. All right, so let me swap. Let me go black here, and let me go red here, positive. And that's exactly how I knew I've got a bad diode. So, and then the other thing that you can check is if you're going across, so across the circuit, across the rectifier, touching both of these, you should basically get double. So I'm only showing half, which is telling me I'm only getting half of the circuit, when this should be reading around 1600. It should be reading double that, because I'm going across both sides of the rectifier. So I'm only getting half, and that's another check to tell me that I've got something wrong with this rectifier. So that is currently what my finding is. Like I said, I don't know why I would expect it's just for ease. That's why High-Tech sells a motor like this. They don't have to worry about attaching a separate rectifier in here, but I don't like the fact that this has brushes in it and I can't get to the brushes. I don't like the fact that it's got a rectifier inside the motor and I can't get to the rectifier. You know, the lesson learned is you can cut smaller rocks and beat, follow the guidelines of using the trim saw, and you won't blow a rectifier. But I still don't like the fact that, if my saw does bind up, I have the potential of blowing this rectifier, and then I've got to replace this I've got to take this apart and change this. So what I'm going to do is I'm probably going to end up, I don't know if I'm going to go with the same rectifier. This is like really cheap. I think you can get 5 of these for like $7 on Amazon. I mean, these are like super cheap. They have a reputation though of blowing very easily, especially because these, a lot of machine equipment for cutting, saws, lathes, this is put in a lot of cheap equipment. And so there are better rectifiers out there. I don't know if I'm going to go with a slightly higher rating. I need to do some more research on how high I can go and still have the same electrical protection. But I just, I thought I would share my learnings here that, like I said, if you're out of warranty and this motor fails, you think it's the motor, you can go back with the same motor, but you've got to be very delicate in how you use this so that you're not overloading this, because this rectifier is in a very difficult place to get to. And also know that you're going to have brushes that are eventually going to wear out, and you're not going to be able to get to it without tearing this apart. So that's just my thoughts on this. I'm going to, like I said, look for a different rectifier. I will probably run my wires externally and not have this inside here, and I'll mount a rectifier outside of this motor in the box. Don't know what, like I said, it's going to be, but I want it to be easily accessible. Even if it is the same size, I want it to be accessible where if I do blow it again, because I am going to push the limits of my trim saw, and I want to be able to have access to this. So I hope this helps some of you that don't want to send your motors in for repair to High-Tech, or even if you don't want to have the same type of motor, maybe this will help you. So keep on rocking, and thanks for watching. Bye. Oh, I forgot I was going to include a shot of what the model rectifier is. So this is an SEP KBBC 1010, KBPC 1010 bridge rectifier. So if you look these up on Amazon, you can get 5 for $8 right now, I think is one of the more popular ones, but they're a dime a dozen out there because they blow that easily. So, and then I was also going to mention that if you do feel uncomfortable with performing, any of this work, you can always just bring it to a motor repair shop and tell them what you want, and that might be also a cheaper option. So just thought I'd throw that out there. All right, thanks for watching. Have fun.